started here. First, some administrative business. Your problem set is due today, and that should go directly to Tom, who's sitting right in the front here if you haven't met him yet. There is a question on one of the problems, and that is the exchange current density for the direct ethanol cell, which some of you just heard a little discussion on, which I think you probably are going to end up with some unreasonable numbers. I heard a lot of different numbers, which is a little surprising, but we're going to get back to that on Thursday. I'm actually going to tell you today why the number that you calculated, if you did it right, should be an unreasonable number, because there's something I've been sort of glossing over so far, ignoring, fudging, if you will, because I didn't want to put in that level of confusion. And somebody actually typed out the whole problem set? Wow. You know, once, a few years ago, I had a professor of mathematics come and ask if he could sit in on audit my freshman chemistry course. I was, on one hand, very impressed with this. On the other hand, very nervous about this, because you know, typically when you're doing chemistry-type math, you cheat a little bit, and having somebody who knew what you were doing sitting in the audience was potentially a problem. Although he was very nice to me, I have to say. The one time I screwed up big time, he didn't tell me in front of the class. He waited till afterwards. Anyhow, he would do the homeworks and the whole thing. He really wanted to learn chemistry. And he did his he turned in his homeworks in tech. They were word process. And I would just take his, no, it was great. I'd take his homeworks and post them as the answers. He didn't make a mistake. The only time I ever caught him up, he took the final exam, and he actually made a mistake on the final exam. I was so impressed that I could finally find something. Oh, he did the whole thing. He did. In fact, he insisted on doing the lab. He said, you know, I'm a pretty smart guy, and I could sit here and read the book of, you know, that's all it took to learn chemistry. And the only way I'm going to learn chemistry is actually do it. So I want to do the lab also. So he was a great guy. Came up at the end of the term and said, you know, he said the difference between freshman chemistry and sort of a you know, a freshman calculus course, which he might teach, is that we get to do all these wonderful demonstrations and blow things up and color changes and whatnot. And when he says he's going to do a demonstration in his class, you know, it's some elegant solution to a differential equation, it just doesn't seem to have the same impact. But that's the way it goes. Okay, so we have the homework is due. We will, again, if you're having a problem with the direct ethanol exchange current density, no problem. We'll talk about that on today a little bit and on Thursday a little bit. The next problem set I'm going to delay. I was going to give it to you today, but I'm going to delay till Thursday. I don't think anybody will be too upset about that, so let's do the following Thursday. And the reason for that is I will be out of town Friday and Monday. I have to go back to Princeton and do some work there, and I would rather have you have some chance to talk to me after you've looked at the problem set before you turned in. So I'll delay that till Thursday, and it'll be due the following Thursday, and I'll be around on Tuesday and Wednesday. Okay, one other item of administration. Because of some commuting issues and whatnot between Caltech and Princeton, I need to sneak in 2 lectures that will not be on the regular Tuesday, Thursday schedule to make this work. And they're going to occur the week of February 6th. And so we will have the normal Tuesday, Thursday lecture that week. But in addition to that, you get a double dose of me on the Tuesday. Was that the 7th? So we'll do the 1.5 hours. We'll take a little break, and we'll do another period of time, if you can take it. And then we'll also meet on Wednesday that week, the 8th, and in the afternoon, I believe at 2:45, but I have to double check the time on that, and have a lecture then. And then that means you get out of a week of lecture, so to speak, later on. You don't get out of it because you've had it, but you get a week off. Okay. So now to chemistry, electrochemistry. And again, for those of you, we're switching over to a new board system. So if you see me dancing around here today, that's because we have a new recording system on these boards, and we'll see how that works out. And if you hear Tom yelling at me, no, don't do that, that's also because of the board system. That's the bad news. The good news is I can use all these different colors of markers now. So And they're regular markers. They're not electronic anymore. All right. So all term, I keep on reminding you that when you do electrochemistry, you have this unusual problem in chemistry, and that is the reaction only happens at the electrode. And so we have to get the molecules from way out in solution up to the electrode surface. And it's now time to deal with that problem. So we'll spend probably most of this week dealing with that problem. I'm going to start this off in a very sort of qualitative way and sort of give you a feeling for what's happening, and then we'll work the problem correctly after we've kind of jumped through it and made some gross statements and whatnot. But let's start off by, first of all, saying we're going to be working in the opposite regime of where we were working when we talked about the Tafel equation. That is, obviously, in the case of the Tafel equation, the kinetics is the rate-limiting thing. That was the whole trick there. Now we want to go to an extreme where as soon as a molecule gets up to the electrode surface, it gets oxidized or reduced. So the rate-limiting process now will be the transportation of the molecule up to the surface. And things are going to happen so fast once that molecule hits the surface, we never see that. Okay. Now what that's going to lead to is, although we normally say that the Nernst equation is an equilibrium statement, which it is, and therefore if you're at equilibrium you wouldn't think any current is flowing, I'd make the claim that the Nernst equation will hold right at the electrode surface under this condition where the kinetics don't come into play. That is, the molecule will come up to the surface, it will collide with the surface, and it either will get oxidized or it will not get oxidized. And the only thing that will determine whether it gets oxidized or not oxidized is the potential of the electrode. And so the Nernst equation says at this potential, 10 molecules should be oxidized and 10 should be reduced. That's what will happen, or it'll happen instantaneously. Okay. On the other hand, if the Nernst equation says that everything should be oxidized, then every molecule that hits that surface will be oxidized. So it's just the potential of the electrode now, and that means that we're Nernstian, even though we're not in a traditional equilibrium state of no chemical reaction occurring. That's number one. Number two is we have to think about now how we're going to get the molecule from out in solution up to the electrode. So we have at least three possibilities for doing that. First possibility is it might be by migration. So migration, I'm talking about the fact that we have a charged particle moving in an electric field, and of course I can tell that particle where to go based on the electric field that I'm dealing with. So in other words, there's an electric gradient here, a potential, and there is a charged particle. Possibility number two is diffusion. Of course, that would now involve, instead of an electric gradient, a chemical gradient. And now we're just looking at changes in concentration. And the third possibility is convection. That is some sort of active transport. Lots of possibilities here. So for example, I might stir the electrolyte. That would be one way of convecting my molecule from point A to point B. I might apply a thermal gradient of some sort in the electrolyte and get convection due to a moving thermal wave through the material. I might go and build a jet and have my electrolyte shooting through that jet and impinging on the electrode. There's all kinds of ways I could do this. Okay, so this looks like one thing, but it's a whole bunch of different things. Now, of those three general categories, the first one is the only one that's problematic. On the one hand, would think this is good news. I mean, we're doing electrochemistry. We obviously have electric fields and therefore potentials, gradients. We're going to have a charged species in at least one oxidation state. So why not use migration to transport our molecules to the electrode surface? So the first problem is, of course, really what I said was a plus, and that is you need to change the oxidation state of the molecule if you want to do electrochemistry. So I can guarantee that the molecules don't just have one kind of charge on them, but there's at least two different states they're in. And in fact, one might be neutral, and of course that would be a problem. We can't get migration to occur if we have an uncharged molecule. But even if it is charged, it's changing charge. So the rate that we will be moving molecules either up to the surface or away from the surface will be different depending on exactly what charges we're dealing with. Of course, if we're going to depend on this, we could also be in the unfortunate situation that the potential that we have to put the electrode at in order to do the redox chemistry is such that the electric field is repelling these ions from that area. So migration is going to be very hard to control in this system. It's going to be variable, and that's one thing we don't want. So typically, we like to avoid migration. And this is another reason why we're going to use a serious dose of supporting electrolyte in our system, because the supporting electrolyte gives us a lot of charges in solution, which minimizes the extent that the double layer or the electric field extends into the electrolyte, and so we don't have huge migration terms in that system. So this is something we want to avoid. Diffusion is going to be the one that 9 times out of 10 we're going to use for our method of transporting molecules up to the surface. It's more or less built into the system, right? You're going to sit there with an electrochemical cell. You're going to oxidize, let's say, something at the electrode surface, and in doing that, you will deplete the electrode surface of the molecule in its initial state, and therefore you've got a built-in chemical gradient from whatever it is out here in the bulk solution to the electrode surface. So you have a beautiful chemical gradient to move things down, and so that's built in. So that's typically what we're going to use. Convection, on the other hand, though, is used, and the classic probably example of convection, I've already given you a couple. There are these jet electrode systems and whatnot, but the classic example of convection would be the rotating disc electrode, where one goes and generates an electrode, which is a cylinder which has a piece of metal typically. There's your electrode down here, and some kind of a contact that we can rotate around. So we can have a mercury junction in there, we can have brushes in there, something like that. And so if we're looking at the bottom of this electrode, then we have an insulating region and a conducting material in the center of that, and this is going to rotate. And as we do that, then, we are going to move material up from the solution like this. And if we do this in a very controlled manner, then we can control the rate that we transport material up to that surface, and then, of course, the rate that it moves across that electrode surface. So it's a good way, as long as we have very good control over rotation, of providing a specific environment that we can define that moves material up to the surface, and we know exactly how much, as we know the hydrodynamics of that system. So in the diffusion case and in this rotating disk case, we have a well-defined system. Okay, so how are we going to look at this system then? Independent of which one of these three things actually you want to use. Yes?
I have a question about the rotating disk electrode.
Mm-hmm.
So you're using that as your working electrode?
Correct.
Okay, so then how do you incorporate your counter and your reference?
Okay, so the question is, the rotating disk electrode's the working electrode. How do we get a counter and a reference electrode into this system? They do not have to be anywhere near this disk electrode or moving with that system. Now, why that is, I would like to delay the answer to a little bit later today. Okay, we should get to that, I hope. But you could use a standard reference and counter electrodes far away, if you will, from this electrode. By far away, the caveat, remember, is still that the reference electrode is somewhat close to the working electrode, but far enough away so it does not perturb this nice flow pattern that you want to develop there. Okay. So, for example, you would not use a Luggins capillary in this system, because the idea there is to get the electrode really close to the working electrode, and that is certainly going to mess up the flow pattern. Okay. But typically what you would do is use a counter electrode, which would be a flag electrode, so a flat piece of metal, platinum, say some distance below that, so again it doesn't mess up this convection. There might be a couple centimeters here. And a wire out here, of course, to connect into your circuit, and your reference electrode way out of the way. And in fact, it's not so bad if you simply had as your counter electrode not a flag, but a sufficiently long wire somewhere else in the cell. Okay. Now, why that all works, I will get back to, but pragmatically, that's the situation. Okay. Of course, if we're going to discuss this, we need a chemical reaction. And so we're going to go to our standard reaction, exciting reaction, an oxidized molecule plus n electrons going to reduced molecule. If all I need to be concerned, I've jumped a point here when we got to that question, whether we are going to use some kind of active transport, some mass transport like I've shown you here, or diffusion, or even a migration, then I'll just stipulate that any one of those processes can be characterized by a single constant. It's a pretty good statement. Okay? In other words, if I'm looking at diffusion, then there's a diffusion coefficient that tells me something about how a molecule will move down a gradient. If I'm looking at some sort of active mass transport, then there is some other kind of constant, some sort of a mass transport constant that would explain how a molecule moves from the bulk to the solution. But I'm assuming there's one constant, and we'll call that constant m for mass transport, independent of what it is. And I have to realize that m might be different from my oxidized molecule than my reduced molecule. So I have an MR and an MO. Now, this is going to become an important point in a few minutes, because typically we assume that these two numbers are the same, are very, very similar. And that's okay as long as the oxidized molecule and the reduced molecule look about the same. Okay, if all I'm doing is pulling an electron out or putting an electron in, nothing else is changing, then probably those two numbers are about the same. But you do get yourself in a situation where maybe when you pull an electron out or put it in, you break a bond, and you make a new molecule that looks very different. And then this assumption can start to break down, and it's easy to forget that that's the case, because we're going to bury these numbers. Okay, so keep a track on what's happening there. Okay, so we have two coefficients that are going to describe our mass transport. The second comment to make then is there is some sort of a rate for bringing molecules up to the electrode surface. So in this particular case, we want to bring oxidized molecules up to the electrode surface and reduce them. And that rate is going to depend on the gradient that's available at the surface. So I'm going to refer to that rate, so I don't have to write rate all the time, as just transport here, new transport. And that would be equal to, for the oxidized molecule, say, the concentration of the oxidized molecule as a function of distance, and I'm interested specifically at the electrode surface for that. So in other words, if I'm carrying out the forward reaction written there, and I have an electrode sitting here in position where the electrode is at x equals 0, and x is getting larger this way, and I map on this axis concentration, then far away from the electrode, I'll be at a concentration which is the bulk concentration. Remember, I'm using an asterisk to indicate I'm at bulk. And then at the electrode, since I have no charge transfer limitations, depending on what potential I'm at, I will reduce this molecule. The number I reduce just depends on the Nernst equation. And so I will have fewer of these oxidized molecules at the surface. I don't know exactly how many, but I'll have some surface concentration here. And so I predict some kind of a gradient that looks like that my molecules are going to move down once the process gets started. So really what I should be looking at is this derivative, but we won't do that. Instead, let me just say that this transport, to make life simple, is proportional to my mass transport coefficient, again for the oxidized molecule, since that's what I'm bringing up to the surface, times the difference between the bulk concentration of the oxidized molecule and the concentration at the electrode surface. Right? So I'm simply saying that I can take a difference here in place as a decent approximation of that derivative right there. Now, let's get this in terms of current. So we'll look at current per unit area, or current density, since obviously the current will increase with the size of the electrode. And I have been arguing all term that that is simply the rate of the chemical reaction times some coefficients here that are going to get us in the right units. So it's the change in the concentration, in this case oxidized, as a function of time. And that, again, is evaluated right at the electrode surface. That's the only area that I'm interested in. And if my current is just this transport rate over here, then I have the situation for a mass transport limited that the current, therefore, is equal to this rate, excuse me, not constant, but rate, and that's going to be equal to our coefficient here times the concentration gradient evaluated at the surface. So that's a statement we're going to come back to. Yes?
I'm sorry, is that F the same different from Faraday's?
This is the Faraday. I've gone and changed my nomenclature. Thank you. Yeah, that F is, in fact, the Faraday F. Okay. And I'm trying, after reviewing what was coming off the board before, I've decided a regular F may make life a little simpler. So I'm going to switch over to a regular F. That's just Faraday's constant to hopefully help the resolution on the board. And to confuse you a little bit. Okay. So what we have then is that the current divided by n, Faraday's constant area, just to move all those constants over to one side of the equation, is equal to negative of that mass transfer coefficient times the difference between the bulk concentration and the concentration at the surface. Why a negative sign there? You'll notice this is a positive number. That is, since I'm carrying out a reduction of the oxidized species, the smallest this number can be is 0. That is, the concentration is the same anywhere. And if any molecules are oxidized at all, then this becomes a more positive number. But it's a reduction reaction, and we've defined reduction reactions as having negative currents associated with them. So I throw in a negative sign here for the sign convention. I could write a similar statement for the reduced molecule that I am going to generate. That is, the current also could be stated to be, and this is the same current, just the mass transfer coefficient times the difference in concentration between the bulk concentration and the solution concentration. Now you'll notice if we are carrying out this particular reaction that I've written over there, and assuming we start with oxidized and we're turning it into reduced, then we're making more material at the electrode than we started out with in the bulk, and so this difference is a negative number. Okay. So I have two negative numbers. That is, this current and this current are the same number. Everything works fine. Now typically, when I'm doing this experiment, the way I would do it is I would have only oxidized around, and as time went on, I'm making some reduced. So I'm going to make the assumption that at time equals 0, the bulk concentration of the material is 0 when it's the reduced material that I'm talking about. And although you can imagine an experiment where you would intentionally go and pour both the oxidized form and the reduced form of a molecule into an electrolyte, 9 times out of 10, this is how we're going to run the thing. And then you can see in that case, current that we're dealing with is just minus mR times the concentration of the reduced material at the electrode surface. And look at that, I didn't do what I said I was going to do. Oh well. I'll get out of your way in a little while. Okay, next question we could ask, looking at this statement right here, is what is the absolute largest current that we might get out of this system? And you can see the largest current is going to occur when that's 0, right? This is whatever you put in, and obviously if you make that bigger, you better get a bigger current. But once I've set up my electrochemical cell and put in some concentration of my oxidized molecule, then I will get my largest current here when that value drops to 0. Okay, so in that case, we can define a limiting current, I sub L, and we have to divide that again by NF and A, which is just this value when every molecule that strikes the surface is instantaneously reduced, right? So I have no concentration there, or just, and I drop my negative sign, which I did not mean to do. Can't get a bigger current than that there. Okay, so to make life simpler, what I'm simply going to do then is I am going to ratio my currents against this limiting current, which will help us get rid of all these little constants that are floating around, so I don't have to write them out all the time. That is, instead of just talking about the current, the concentration at the electrode, let me talk about that concentration divided by the bulk concentration, and that is equal to 1 minus the current divided by the limiting current. So all my NF and A's disappear, and I have a nice simple statement now. That relates my current to my limiting current in terms of the bulk concentration and the concentration at the electrode surface. Or, of course, solving this so I can get back to my surface concentration. At the surface, the concentration of oxidized is just the limiting current minus the actual current divided by N, mass transfer coefficient for the oxidized molecule, Faraday's constant, times the area. And I'm throwing those guys back in because I'm going to make them disappear in a second. Okay, and can you see if I write down here? Is that legible? I noticed when I was writing at the bottom here, people were kind of, okay, we're okay. So let me just point out that what I'm talking about pictorially then graphically, is again, in the case where the current is the limiting current, if I make a plot of concentration versus position, I'm going from the bulk concentration down to 0. So all I'm really saying is that's the biggest gradient I can build at an electrode surface. I can go from some bulk concentration out here down to 0 at the surface. That is, every molecule that strikes the surface instantaneously gets turned into reduced. So there's never a population over here once the experiment gets started. On the other hand, since I have argued that this is a Nernstian type of system, I might find myself in a situation where, say, I is equal to just 1/2 of the limiting current. And I can choose that by choosing the potential somehow to be correct. And then I'll generate, again, a situation where I have a gradient, but it will not be as large a gradient. That is, I'll go from my bulk concentration down to some value here at the surface. That still leaves a population here. Okay, so that raises the question, well, exactly what is the relationship then between the potential that I've applied to this electrode and the currents that I'm talking about here? I'm moving. I am now going to, can I erase these boards now?
Yeah.
Okay. We're going to move back to this board. I'll race over here, keeping myself busy while Tom takes a nice picture on the right-hand side. Okay, so we have the statement way over there that tells us about the oxidized species. I can write a similar statement about the reduced species. And again, I'm going to assume that all I do is dump the oxidized molecule into solution. So I guess we should keep our wonderful chemical reaction up here. And so at time equals 0, I'm assuming that this is at the bulk concentration. That's a great assumption. And maybe not as good an assumption, but reasonable, and that is 0, that you're not going to go and throw any reduced stuff in. And we could handle it if that wasn't the case, but throwing zeros in makes the arithmetic very nice. Okay, so we've already seen then that the concentration of the reduced species is equal to minus I over NFAMR. Why minus? Again, the sign convention is going to get us into trouble if we're not careful, and that is, remember that this current is a negative current, right, from over there, and obviously I don't want my concentration to be a negative number, so I have to throw a negative sign in there to get things to work out, and all these constants down here are obviously positive numbers. And we already have, let me just duplicate it over here, that the and I should state in here that this is at the electrode surface, the concentration. I'm going to duplicate just what I wrote over there, that for the oxidized species, we have the limiting current minus the actual current divided by NFAMR. Now, I've already argued that right at the surface, under this condition where there can be no charge transfer limitation, that the ratio of oxidized to reduced is given by the Nernst equation. Is everybody happy with that one? Not a problem. Good. Over here? Oxidized at the surface, yeah. O. And at 0. Ooh, thank you. Oh, this is the beauty now of this new system. I can make a mistake and it's not recorded for posterity until you've corrected anything. So by the way, if you do see things like that, please point them out, and in particular point them out before Tom takes a picture, and then I'll look really good, okay? Thank you. All right, so we have the Nernst equation. So we have an electrode potential which is equal to the equilibrium potential under this condition of infinitely fast charge transfer rates. So that's equal to the standard redox potential for the system minus RT over N. We're going to, too fast there. Over NF times the log of the concentration of reduced material at the electrode surface divided by the concentration of oxidized material at the electrode surface. Okay, now this gets us back to what I was saying at the very beginning of the hour with regard to the problem set and the value of n. Okay. In this case, the value of n is pretty straightforward. That is, it's defined by this equation right here. Whatever stoichiometry is needed to make this equation mass balanced, that's the value of n. And I believe for the direct ethanol system, most or perhaps all of you hopefully figured out that that's 12, the way I set up the problem. That same n apparently shows up in the Tafel equation that I wrote before. Tafel himself didn't have a problem with this because remember, Tafel was looking at the interaction, the reduction of water to make hydrogen, and the oxidation of hydrogen to make water. And that can be thought of as a one-step process. Okay. So the stoichiometric n and the n in the Tafel equation are the same thing. But as soon as we look at something more sophisticated, we know that there's a reaction mechanism that goes with it, and it might be a multi-step process. So for example, taking that case of ethanol, it is exceptionally unlikely, in fact, I think we can rule out the possibility that when an ethanol molecule strikes an electrode surface, 12 electrons jump into it. Okay? So even though that is the stoichiometry of the reaction, there clearly is a set of steps, and maybe one electron goes in, and then in the second step, maybe 2 electrons go in, and you might imagine in some very far-fetched system, maybe there's a step where 3 electrons sort of jump into the molecule, but even that's pushing it. People really haven't seen evidence for anything more than a 2-electron charge transfer in sort of simultaneous process. When we have a mechanism, of course, kinetically, all we can see is the rate-limiting step. Right? And so assuming there's a multi-step process, then the n actually that we need to put in for the Tafel equation is the number of electrons in the rate-limiting step. Now, you, of course, have exactly 0 idea of what that might be in the direct ethanol system, and that's why I set up the problem to use the stoichiometric number of electrons, and that's probably why we're getting a really bogus answer. But it is more likely that the answer, I don't actually know what the answer is either, because the mechanism for direct ethanol oxidation is still a little bit ambiguous, but it's more likely that n equals either 1 or 2 in that system and not 12. Okay, because all we see is the rate-limiting step. But for this, since there is no kinetics, the n that we put in is the actual stoichiometric n. Okay, well, we have an equation here that gives us potential in terms of concentration. We have currents in terms of concentrations here. So we can plug the two into each other, and we can come up with a statement that gives us a current potential relationship. So we have that the electrode potential is equal to the standard redox potential, E naught, minus RT over N, Faraday's constant, times the natural log of MO over MR times I over IL minus I. So I have put, using the standard nomenclature, reduced over oxidized, just like I wrote it over here. So that flips some things around here. let me point out to you again that if you are looking at an older derivation of this equation, typically the equation was written, the chemical equation was written in the opposite direction, and so you'll either see it written the way I've written it, but with a plus sign over here, or you'll see the negative sign over here, and the quantity in the log flipped over. So don't be confused if you see that. If I now go and make a plot of that, where I'm now looking at the electrode potential and current over here, those of you who are used to doing pH titrations immediately see that I have a sort of sigmoidal shape here. This is your standard pH titration curve with the logarithmic term. And so I'm going to have something that looks like that in it, where this is my limiting current. I'm looking at absolute value of current, yeah. Thank you. Now, those of you who are less chemically oriented and perhaps more mathematically oriented have noticed that we have a problem with this equation right here, and that is things get rather ill-defined when the current is the limiting current. And then my denominator here blows up. And so how can I say that that's the limiting current over there? So I really should specify that this equation holds for I less than the limiting current. And then I would just argue what we need to look at, of course, is the limit of this term as I approaches IL. We'll get this value right here when we do that. And clearly, we can't get a limiting current that's larger than the limiting current. That is the limiting current, and therefore this has to plateau at that point. Now let me define a point on this curve where I hit half of the current level of the limit. So this is I equal to I sub L over 2. And then there's some potential that's associated with that. And I will define that potential as E1/2, or the half-wave potential. Well, let's look at what that corresponds to. So I can plug in for my current up here, half the limiting current. So under conditions where I equals half the limiting current, then I have that my potential is equal to standard redox potential, E naught, minus RT over NF times the log of the ratio of the mass transfer coefficient for the oxidized divided by the mass transfer coefficient for the reduced, plus RT over NF times the log of IL minus I divided by I. Okay, so I have taken the log term and I have separated it out into two terms over here. And in doing that, just because people seem to like plus signs, I flipped this term over so I can have a plus sign right there. Okay. And now I will say, under this condition of having the current being half the limiting current, my potential is the half-wave potential. That was my definition of it on this graph over here. So I now have defined the half-wave potential. And now I'm going to say, well, typically, the mass transfer coefficient for the oxidized species and the reduced species are very similar. And so this term is going to disappear more often than not. That is that MO over MR is approximately 1, so I'm taking the log of 1. And so I don't have to be too concerned about that term. The way I'm going to handle that, though, is I don't want to... All right, Tom, I'm going to work over here so you have a free shot. I don't want to totally ignore that term. Get myself into a little bit of trouble doing that. So let me then just define E1/2 is equal to the standard redox potential minus this term. And then I have the statement that the potential of the electrode is equal to the half-wave potential plus RT over N, Faraday's constant, the log of the limiting current minus the actual current divided by the limiting current. So there's our relationship. So far, everything I've done is true. No problem, right? I've left my current dependence in there. I've defined an E1/2 under a specific condition over there. And so it's an absolutely true statement. And here's where we do the sleight of hand. If we leave it there, everything's fine. However, what if I say this, that the standard redox potential is approximately equal to the half-wave potential? See, that will be a very good statement as long as this term is insignificant compared to this term over here. Okay. And that's typically what we do. And 9 times out of 10, it'll be fine. And the 10th time, you'll have messed up big time, right? Because, again, the molecule has changed dramatically between the oxidized state and the reduced state, and it's not diffusing through this. To get a feeling for this, a typical number for a molecule diffusing through solution is for the diffusion coefficient, d, that goes with that, would be on the order of 10 to the minus 5 centimeters squared per second. If if you're walking down Colorado Boulevard and someone walks up to you and says, "What's the diffusion coefficient for ferrocene and acetonitrile?" and you have no idea what the answer is, just say, "Oh, it's about 10 to the minus 5 centimeters squared per second," and they won't bother you anymore. It's a good number for things in solution, okay? On the other hand, yeah.
So let's assume it's like a perfect reversible reaction.
Mm-hmm.
And how much difference will irreversible reaction make?
Okay, now a huge difference, because remember the whole assumption behind this is that there is no kinetic limitation, and of course in the irreversible reaction there's going to be a kinetic limitation. That's the definition of an irreversible reaction. So that's going to change things, but let's consider how it's going to do that, but give me a couple minutes to develop that, okay? So we have to look at that certainly, because the assumption is that is not happening at all here. Now, staying with that diffusion just for 1 second, let me just finish that one thought I had. To give you a comparison, if I'm thinking about a molecule diffusing at room temperature through a solid state matrix, okay, then the sort of numbers I'm going to come up with are on the order of 10 to the minus 10 centimeters squared per second. Okay, so you can see in solution, if you pick one molecule versus another molecule, it might be 2 times 10 to the minus 5 centimeters per second, and the second molecule might be 10 to the minus 6 centimeters squared per second, or something like that. But that is such a small difference compared to what you would have, say, in the solid state for diffusion, that we can consider both these sorts of numbers about the same and not affect this dramatically. Now, there's a question.
Yeah, I'm sorry. I missed the connection from the E1/2 here to up above. Is it?
Yeah, these are the same E1/2, right? It's a situation. What happens over here? I should have written this out, perhaps. You may want to record this one. I left this a little ambiguous, right? Let me. Remember my better penmanship here. Hold on. You got the point, but for the picture, we want it to smile nicely. Right? So this term disappears on us. This becomes 1 under this particular condition, right, of half the limiting current. And therefore, U1/2 is the same there. Thank you, because I did sort of gloss over that point. OK, so this is fine. And then we make this assumption. And it's not a bad assumption, except when it's a bad assumption. But usually it works. You can get away with it. OK, now that actually brings it. Yeah.
For say for ferrocene or something, what is the actual ratio of the oxidized to reduced? I mean,
The problem is, and you'll appreciate this better than most, Bruce, that measuring diffusion coefficients isn't easy. And so, one of the reasons that this approximation is made is that we typically cannot measure the diffusion coefficient well enough that we could tell that they're different. I mean, at the point that you make a measurement and say, oh, the oxidized species has a different diffusion coefficient than the reduced species, it has a very different diffusion coefficient. So a diffusion coefficient difference of 10% is really not measurable, even on a good day. And it's got to be more on the order of magnitude difference before you get that. And of course, an order of magnitude does start to have an impact then on a log term. But that's what it takes. So there is a pragmatic reason for doing this, and that is until that diffusion coefficient really changes, order of magnitude change, you're not going to pick up the fact that E1/2 is different from the standard redox potential. And so if you were assigned the job of making up the table of standard redox potentials, you wouldn't want to do it this way. Right, because it doesn't have enough accuracy to get 10 significant figures for the standard table that everybody's going to memorize. And you want to do it actually by some sort of a direct titration technique where you can get a lot of accuracy and precision in the measurement and the reported number. But if your job is just to look at a molecule and say, what's its redox potential to within, say, maybe a tenth of a volt, then this is going to be a great approximation. And typically that's, from a pragmatic point of view, that's what we're interested in. We're not interested in voltages, potentials that go beyond that. OK, so this gets down to the pragmatic issues. So based on this discussion, the first, what good is this? The first thing you could do with this, if you had this set of data, if you had this curve right here, then quite obviously you could assign a redox potential for a molecule by using this approximation. It's easy to find the half-wave potential. And so one thing this gives us is redox potentials now with all the caveats that I just pointed out. And let me point out to you that this is a standard redox potential. In fact, I think we've got to write standard. That is, the number I am getting out of this experiment is the redox potential when I have 1 molar concentrations of oxidized and reduced present, and when I have 1 atmosphere of pressure, and when I have room temperature. OK. Now, I'll point out to you all these equations, even though I write T here, actually assume room temperature. So you have to put in the 298 degrees Kelvin that goes with that to make that statement true. But the interesting thing is that I didn't put those concentrations or pressures into the cell. In fact, I have a cell sitting there that has a lot more oxidized than reduced in it, and whatever the pressure is. And yet, the value I'm getting out is the standard value when under standard conditions. So it's directly comparable to what I would read off of the table. OK. Next thing you'll notice is that if I were to make a plot of the log term, I'm going to switch over to log base 10 because that's what most people do. And you'll recall that that just changes my natural log by a factor of 2.3. So we'll take that into account. In fact, I'll make it explicit. I'll put the 2.3 there. if I make a plot of the log of this current term versus potential, then that should be a straight line according to the equations I've written here, and I should have a slope of RT over n Faraday's number, and that will equal 0.059 millivolts over n when T is room temperature.
You gotta get rid of that 2.3. I mean, once you
No, the 2.3 has to be there. That's why I did it in those.
No, you don't want
What?
you want to plot just log.
Excuse me. Yes. All right. The point Bruce is making is the 2.3 is incorporated in this number here. If you don't plot just log, thank you, Bruce, you'll be off by a factor of 2.3. What? The log of this term versus e is linear, right? According to this equation. And that's the slope of it, right? 59 millivolts.
It should be 59 millivolts.
Oh, excuse me. Thank you. Whoa, yes. I was being so clever here in writing it in volts so I wouldn't confuse anybody, and then I wrote millivolts next to it. Yeah. Or just to be explicit here, 59 millivolts over n. Okay. Now, this gets back to our Tafel and our question a moment ago. First thing about this is, of course, if I don't, for some reason, know what n is, I can back n out of this, okay, assuming that I'm certain that I'm diffusion limited or mass transport limited in general. Okay. If I do know what n is, then I can use this as a test to see if, in fact, I meet the condition of being mass transport limited. And typically, I would know what n is. Okay, so in other words, if I make that plot and it's not a straight line with that slope, I'm not mass transport limited. Okay. What will actually happen, if you look at that plot that I'm suggesting you make there, that's something very similar to the Tafel plot, right? And the Tafel plot is log of current versus the overpotential. Okay, and the overpotential and this number scale with each other, right? So in the Tafel equation, I'm going to expect a similar straight line dependence if I, instead of being mass transfer limited, I am charge transfer limited, then Tafel will have a slope that's equal to RT. Here's my ambiguous NF. I'm going to put a little alpha down there, and I have to throw another alpha in. Okay, so it'll have a different slope. First of all, it'll differ by this term alpha, which is the symmetry of the barrier. But remember, that's probably 0.5. And second of all, and now that's why I put the alpha down there, it will be affected by this number n. Okay, so you can see, in the case of direct ethanol, taking that as an example, if I mass transport limited, then n equals 12, the stoichiometric value over here. If I am charge transfer limited, then n is either going to be 1 or 2, depending on exactly what the mechanism is. And so that makes a huge difference in this slope. Okay, which is probably was the problem. There's the solution to the problem. But experimentally, what does this mean? It means that if you make that plot, you can immediately tell whether you're in the Tafel regime or you're in the diffusion limited regime. Now, of course, there can be situations where you're not in either regime, but again, the slope will not be 59 millivolts per decade of electron there. So you'll find out. And then finally, what you can do with this is if you develop this whole curve, then you can back this limiting current out. And so you can make plots of concentration, bulk concentration, versus limiting current. And from that, you can come up with that mass transfer coefficient. And again, given the limit to which you can determine a concentration, and given the limit to which you can record a current, you're not going to see 10% changes in this number. Right. Okay. Now, let's go back. Any questions on this?
How dependent are all these results on the linear concentration gradient?
It's totally dependent on it, really. And we're just looking at it. In other words, so what I'm saying by all this, and I think you can take a pretty picture of the right-hand side, Tom. What I'm saying is that the reason we have a current at that electrode is because of the existence of that concentration gradient, and the bigger that concentration gradient is, the bigger the current is. So it's the only parameter affecting the system.
So for different functional forms, we're going to have completely different treatment.
Assuming you did not have a linear gradient there. Now, it's going to turn out, as I will show you in 1 second, it's going to be very hard to get away from this kind of gradient. Okay. Yes? 2 is a base 10 log. Yeah, there's a factor of 2.3 in there. I wrote this all out in terms of the natural log, because typically when we're doing kinetics, we're taking derivatives, and so we're dealing with natural logs. But that logarithm originally comes, remember, from the statement of the Nernst equation. And when Nernst stated the Nernst equation, he used a base 10 log. So for different things, we have this tradition of using the natural versus the base 10 log. And that 59 millivolts, which keeps on popping up, is always based on a base 10 log. Okay, I'm going to leave where I can clear out this right-hand side. Leave that left-hand side up there. Can use that a little bit more. Let's go back to the rotating disk electrode, which is a germane in light of what kind of diffusion gradient do you have. Now, I would suggest to you that it would appear that the two extremes you could get to, on the one hand, you could have an absolutely quiet solution, and you'd have a beautiful diffusion gradient in there. And on the other hand, you could have this rotating disk situation where you're actively transporting material up to the electrode, and you would think that you would establish a very different gradient in those two cases. That those should be sort of night and day examples. But in fact, the way you operate your rotating disk, draw that out. Here's our disk again, and it's rotating, is you make that surface as flat as possible. In fact, it's a polished surface. And the idea is that we will have laminar flow of the solution over here. And so what that means is if I were to break my solution down into little differential elements, that I would have a situation like this, where I'd have these elements, and the first element, if you will, sticks to the electrode. It moves with the electrode. The next one's slightly displaced. And of course, I'm allowed to make these small enough that this is true. Okay, so that is the assumption for laminar flow. It's very smooth. And it turns out that all the hydrodynamic equations that one develops for a rotating disk electrode are under this assumption. Okay. So what can go wrong with that assumption? Well, if you don't have a very smooth surface, or if you simply rotate too fast, then you'll get turbulence building up in the solution, and this situation will no longer exist. This turns out to be a really important thing if instead of doing electrochemistry, you decide to build airplanes. Right? You don't want turbulence going over the wings. And so there's been a lot of engineering work done on hydrodynamics for airplanes, boats, things like that, that tell you when the turbulence will set in, under what conditions it'll set in. And systems are rated with a number called the Reynolds number that comes out of these equations that tells you at what point you'll come up with turbulent flow. And so we're going to always assume that we're below the Reynolds number indicated rate in these systems. I happened to mention to some of you yesterday that Professor Lewis at one point, well, we were having a problem actually with a kinetics in a system that we wanted to study using a rotating disk system, and he said, well, if we could just rotate fast enough, then we could get over this problem. And so his proposal was to go and get a VW bug. These are the old bugs, not the new bugs. Engine, it was his proposal, and strap it to the wall, and he decided that that could be geared down, and we could go at 2,000 was his calculation RPM with the right gearbox on that thing. And you're going to have two problems with that. We never did it. Number one is you will exceed the Reynolds number of this solution if you do that, so it doesn't matter that you can rotate at 2,000 RPM. Second, those VW engines didn't exactly run super smoothly, so you will exceed the Reynolds number quickly because of the vibrations that you're going to introduce into your cell. So you want to have a situation that looks like that. Okay. Now, which means that you can get up to something around 1,000 RPM, though, if you have a nice, nicely polished electrode and everything is perfectly flat there. What does this mean in terms of everything we've been talking about here? Well, if this last little layer of solution is really moving with the electrode, then that means that this flow pattern I was telling you about earlier does not encroach on that last layer. That is, you can think of material as being transported actively up to the electrode until it gets to the last layer, more or less. And then when it gets to that last layer, it's diffusing. And if that's the case, and assuming that last layer is a thickness delta associated with it, then our mass transport number is simply the diffusion coefficient for the molecule divided by the thickness of the layer. And you can see, since I've now let you make the thickness of that layer anything you want, this delta, I can get myself into this regime as long as I'm not in a turbulent region. That is, if I'm having a situation where I am not mass transport limited, I can simply make my layer thinner, and eventually I get to a point where I'm mass transport limited. So if I take the equations that we wrote down here and simply substitute in this for the mass transport coefficient, and likewise this for the mass transport coefficient of the product species, the reduced species, then I have the equations that describe a rotating disk electrode. This curve that I've shown you here is the curve that one gets out of a rotating disk electrode, and one can pull out the half-wave potential and the redox potential from such an experiment, as well as determine the limiting current. Now, the one flexibility that you have here is that I can obviously rotate that electrode at different rates. And what is that doing? That is affecting the thickness of that final layer. So I can adjust delta by rotating at different rates up till this turbulent boundary. By doing that, I'm adjusting the limiting current. So plots of the limiting current versus the rotation rate approximately, it turns out that this boundary happens to go as the rotation rate to the square root, or square root, excuse me, of rotation rate, will tell me what the diffusion coefficient is for the system. That was my point number 3 on this board. If instead of figuring out diffusion coefficients and redox potentials, what I'm interested in is concentrations, and I haven't really stated this, but one should recognize that the very first application of electrochemistry, independent of the technique, has been electroanalytical chemistry, where the question simply is, how much of this stuff do I have in this solution? Electrochemistry is really good at that. That's where your pH electrode comes from, right? And again, I might do that by monitoring a limiting current, and we have equations on the board that will tell me concentration as a function of limiting current. So I want to know how much of this stuff is around. If I happen to know all of the coefficients that I need down here, then I can tell you what that limiting current is going to be for a typical system, rotating disk system, a number for m on the order of 10 to the minus 2 centimeters per second would be typical. And then I can calculate a limiting current based on that. And what I'm going to do is I'm going to assume an area here, my A term, of 1 square centimeter, which is a little bit big, I will admit, for a rotating disk electrode, but it's a correct order of magnitude. They're not square millimeters or things like that. That's about 1/10 of a square centimeter is reasonable. I can calculate then a limiting current for that. That would tell me that my bulk concentration of 10 to the minus 9 molar is quite observable. So I should be able to see nanomolar concentrations on a rotating disk electrode. It's one of the more sensitive techniques that one has available, assuming things like you can put the material in solution, you have enough supporting electrolyte around, et cetera, et cetera. Okay, questions? All right then, the next step in all of this is to do this problem correctly. Okay, that is to make life simple here. Where shouldn't I be standing? Doesn't matter. To make life simple here, I'm not going to write any more on the board today. To make life simple here, I have taken a derivative, a gradient, and just said it's a difference between two concentrations, and that's not quite right. And then I've assumed that I always have a 0 concentration out in the bulk solution, and that I'm always mass transfer limited, and that charge transfer kinetics never gets into the situation. Of those assumptions, the last one's a pretty good one. That is, I can get myself in that situation by either picking the right molecule that does fast charge transfer kinetics and the right electrode that mates with that, or by going to a sufficiently high potential that the charge transfer is limiting. So I can always get myself in that regime. The other assumptions may not be quite that valid. So what we need to do then is go back and work this problem out correctly using an actual flux gradient. And that will lead us then to the chronoamperometry experiment, where we do a potential step, and we'll set it up initially so it's a potential step that is sufficiently big so that as soon as the molecule hits the electrode, it gets oxidized or reduced. So we're always mass transport limited. Unlike what we worked out here, we're going to specifically say the transport of molecules up to the electrode is by diffusion. That's it. And then we have chronoamperometry. Okay, so we'll pick up with that on Thursday.